Okay, guys, here we are exactly where we left off. Again, we had just docked with the International Space Station. I think we're somewhere over Australia, judging by the color. And that looks like a evaporating saline lake. So that might be, I think it's pronounced Lake Erie, so that would be southern Australia. Yeah, I think that's where we are now, is southwestern Australia. I do these things because it improves my reliability in orbit predicts. Yes, that's exactly where we are, and I think that's exactly the lake. So that's pretty good. Okay, so this is the 11th installment, I believe, and I left us docked to the International Space Station because we are going to actually pay a visit to another ship. This is how to go from one orbiting spacecraft to another orbiting spacecraft. This is going to use future cheats because you can't really do this kind of thing when it comes to the real world, what we're about to do. At least right now. Maybe in 2100 we can do it. Here's why, okay? This is our orbit mapped in green, which matches that of the ISS. Now, there's a third spacecraft that's orbiting the Earth, Mir. Now, you might be saying to yourself, wait a minute, I thought Mir re-entered in the 1990s. Well, I say screw it, and so does Orbiter. So, because we like more spaceships, Mir still flies even in 2018. So let's display the Mir Ground Track. And what we'll find is it has magically been shifted down from its original launch inclination from Russia. Mir had a very high inclination because it was launched from a very northern latitude, which is Russia. You can't launch a spacecraft into a lower inclination than your latitude. So if you're at latitude 41 degrees, like New York City, it is impossible to launch a spacecraft into a 5-degree inclination orbit without a plane change in between. So if we look now, this is our orbit. Now if we go to spacecraft Mir and target Mir's orbit, what we'll find is the relative inclination difference is massive. It's about 25 or 26 degrees. So you see all the fuel in that fuel tank? Yeah, most of that will be gone by the end of this episode. So I'm going to explain exactly what you need to do to go from one orbiting spacecraft to another, and then we will be able to play around a little bit more. Okay, so step 1 of 2 is going to be lining up our orbit path so that it matches up against Mir's, and we're going parallel and not perpendicular, which is basically what we're doing now. And then the second is going to be exactly what we did with the ISS, where we sync up the orbits. So what's big about going from one spacecraft to another? Because you really can't do that in our current day and age, given the amount of resources that exist. And the reason for that is because when we start getting out towards the outer planets, it is extremely useful to use mothership and deployment methods. So basically what you do is, because if you're going to explore all the moons of the outer planets, what you would do is you would park a mothership about midway between the higher moons and the lower moons. And then what you do is it's basically a giant fuel tank. So you'll fly down to the lower moons and then come back up to the mothership, refuel, fly up to the upper moons and then come back down to the mothership to refuel, or however many times you need to do that. More so for Jupiter than Saturn because of the gravity field. I can't wait to get out there again. Those moons are incredible. But for now, we're stuck on this giant blue ball doing tutorials. So we just actually crossed, or we're about to cross Mir's orbit path right now. And God, that looks like 80 degrees. So here's what we do, okay? Step 1, you're going to go to select align planes. And this time we're going to target the spacecraft Mir. Yeah, that's 78 degrees. Okay, so the next thing we're going to need to do is figure out what kind of delta V is required. So the semi-major axis of our orbit is going to be 6747. The reason I'm going to do the relative inclination burn up here and not down here is because it costs more if you do an inclination burn lower. Okay, so remember how I said that plane changes were extremely expensive in the last episode and there was no reason to try and take off and then fix the inclination adjustment? When you do a relative inclination burn of 78.1 degrees, it will cost you 10,235 meters per second. In other words, it would actually be more efficient to land on the Earth and then take off again using a different inclination. Yes, I said that right. It's more efficient to re-enter and land and repeat the procedure than it is to change our orbit in this case. But I'm trying to demonstrate a concept here. So what we're going to do instead is we're going to do something called the bielliptic. So what we're going to do is we're going to do a long burn to raise our altitude far away from the Earth. And what's going to happen is we're going to have a really low gravity potential, which will enable us to burn for much less fuel. So what we're going to do now is, because we're actually at an ascending node, this is the perfect time to do this. So what we're going to do is we're going to start
rotation,
configuring our ship to go. Whoa. That's a little bit scary. Our pressure's leaked out. So we're at 93 kilopascal. We're at like 3,000 feet pressure altitude. So that means what we need to do is we need to turn on the supply valve and recharge. So something leaked out. It's a good thing I caught that when I did. Okay, so what we're going to do now is start closing the airlock doors. So we're going to close the outer airlock door first, and that will isolate us from the International Space Station. So why do I want to burn here? Because if I burn here, we have a circular orbit, which means that the apoapsis, the highest point of the orbit, will swing out here to the descending node between us and Mir. As a result, we're going to push the descending node very far away from the Earth, where it's going to be actually more fuel efficient. And I know it doesn't make sense, but trust me, you're going to see it. It really, really, really works. It's kind of like cheating, but it's not. Alright, let's make sure that inner airlock door is closed. Okay, it's closing now, and boom, closed. Okay. So we should be good to go. Let's make sure we're still at 100. And we are. It just got really quiet for some reason. I don't know why. Maybe that was the ISS's sound or something. Okay, so everything is recharged. With both airlock doors closed, we are sealed, which means it's safe to leave the International Space Station. For safety, we're going to turn our lights on. The radiator will stay out. We're going to activate our retros by opening the retro door, and I'm losing time, so I need to get going. Let's go into dock MFD so that we can see where we're going. Or dock HUD, rather. And we should be ready to go. So we're going to pull the scary button and hope that we did everything right. Check.
Undocking confirmed.
Okay. So what would happen is if we didn't have a good seal, notice, you see that? The external airlocks just fall into 0. Because we've just vacuumed out. In reality, if I noticed the air was starting to go out, I would have hit the engines and actually shoved the shove the craft over. Fun fact. What is this NASDA? Anybody know what this NASDA thing is? What it is the National Aerospace Development Agency of Japan. So when they wanted to found their space agency, they were inspired by NASA, so they called themselves NASDA. Now, once they did establish themselves, then they changed their name to JAXA, which is what we know them today. Okay, so what we're going to do now is we're going to turn prograde to the Earth. So we're leaving the International Space Station now, and luckily the direction of flight is away from the ISS, which means we're in a perfect position to do this burn now, and it's time to do it now. Okay. Oops. Alright, so we're going to go prograde, and so that we don't waste any more time, we're going to hit the engines. So what you're going to look here is this estimated thrust time. It should go down for the, say goodbye to the ISS. So that is what it looks like when we go under full power straight away from the ISS. And it goes so fast. Yep, see how it's 470 now? It's going down and down and down. That's exactly what we want. Okay, so how do you know when to stop? Well, this is a good indicator of it. So we say every 650 seconds is about 7 or 8 kilometers. Or no, it was 10. It was 10 kilometers. So now we're down to 5 kilometers per second. So you don't want that to get too low. We'll let it go down to 2 and then cut it off, because remember, we are going to have to kill this velocity later on. There is another way of doing it, but that's kind of really pushing it. That is what happens when you do an aero bank, which can be really dangerous. That's basically where you re-enter the atmosphere and you turn, but you don't move off. So there you go. That's going to save us some time. So plugging into my calculator again. Let's see. And I know this doesn't help you guys out because I'm just using this thing that I built. But don't worry, I'm about to explain it. So basically, the way you can do it is if you can estimate. You need the mass of the ship. So if you go to, and I know you guys can't see this either, if you go to info, it'll default, your pop-up window will default to your focus vessel, and you will see the thruster group ratings vacuum. You want main. You want that value, and want your total mass. So in this case, it's 320 kilonewtons. That's a constant that will never change. The variable is our mass, which is 17,319. And so what we find is we can do 18 meters per second squared with the engine. So you come down here and you say, okay, it's going to take 200 seconds of burn time. So if you do 18 meters per second squared for 200 seconds, that's going to give you about 3695 meters per second. But, and this is where our friend calculus comes on, as we burn, we become lighter, which means the mass, the variable changes, which means as we're burning the engines, we're getting lighter, which means we're accelerating faster. So what we're going to do is we're going to wait until we swing out towards the descending node, and then when we get really high, it'll be time to burn. Ain't this a great altitude to view the Earth from? I love it. Right about here, 20,000, where the Earth is big in the window, but you're not so far out that it's, small in the sky. By the way, note how overpowering the sun is. So this G value that's down here is now 0.99, which means the Earth is accounting for 99% of the gravity. Now, what you'll find is the moon actually orbits less than 50%. And the question is, why is the moon able to orbit the Earth when the sun is clearly the stronger gravitational attractor? The reason is because the Earth is moving around, so the centrifugal force cancels the it actually cancels the effect of the sun. What actually causes the moon to break off from the Earth is when it exceeds the orbital velocity at that location of the sun by such a great amount that it embarks on its own orbit around the sun. So, counting, if you were to count the fact that we have centripetal force, the actual effect of the sun on our orbit is much less than that. Okay, and real quick, concept check. Look at how slow our orbital speed is now. It's about 2,800 meters per second. We would have to induce a perpendicular velocity component to change a vector from flat to 78 degrees vertical with a magnitude of 7,800. Here, we're doing it with a magnitude of 2,800. And yes, we did expend a lot of fuel to get out here. However, you will find that it will actually be more efficient in the long run. Okay, today's not a good day for me computationally. I got the math wrong. So now that's a fault of me entering the numbers into my calculator wrong. So the actual number that we're going to be burning is 2721 meters per second, which is actually basically our current speed. So that's not much of a real burn. So I'm not really worried about running out of fuel. If we come down here, we can actually see we do have 16,000 meters per second left in the tank. And we could have done the ink adjustment down there. But I don't want to, because I can use an opportunity to show you how to do it more fuel efficient. Okay. So we want relative inclination to go down. So we're at a descending node, which means we need to burn ascending, which means we need to activate orbit normal plus. The burn is coming up in just about 25 seconds now, so we're a little bit behind the curve. Okay, let's see. All right, 5, 4, 3, 2, 1, 0, -1. Okay, and we're going. Now look at this rate here. It says -0.443. Usually the rate's about -0.1, and it looks like we're actually inducing some horizontal component to our orbit. If you look, we're actually lagging behind. So I'm actually going to disable this autopilot here, because the autopilot isn't able to track our ascending node as it changes. So why is the ascending node changing? Because we're steering in orbit, and in order to induce a perpendicular component, you have to stay perpendicular to the orbit plane, which is what we're trying to rotate. I know that's a little bit complicated, but if I come outside the craft, basically what we're doing is we're steering, rather than going around, the equator, we're basically, actually it's opposite. Instead of going around the poles, we're going to do it so that we go more level. So if you look, the angle that we're making, if you draw, this is perfect. If you draw the Earth-Sun line, this is an approximation of where the equator is right here. And you see how steep we are compared to the, let me make sure, yeah, we're still bang on. How steep we are to this line, we're actually going to cut that in half. So when we're done, we're actually going to have a line that's much lower. And we're actually almost halfway done, if you can believe it or not. That's how much more efficient this is. So we've already burned just about 2 kilometers per second. And notice your orbital velocity doesn't change, or at least it shouldn't. If it does, it means you're not doing it right, which I'm not. You need to be bang on like that. If you do it right, you won't have any sort of velocity induction, which is what you want. We're getting close. Alright, I'm gonna go to translation here. Well, actually, we're gonna stop the engines first. And we're gonna line straight up. Actually, we can activate the autopilot.
Translation.
We're actually gonna go to translation here because we're far enough out that the gravity is low enough that we can actually translate and get a significant effect from that. So what I'm going to do is I'm going to translate this back until it's more accurate here. Let's check our RCS fuel because I know we've been using a lot. And it doesn't have to be 0, but the lower we can get it, the better. That's it. So that's all we can do for now.
Rotation.
So we're going to go back to rotation. And now you can see we're now down to 12,835 meters per second. So there is something that we could do when we reach the apogee, which obviously the highest point of the orbit. We could do a short burn and lower our perigee into the atmosphere. So then what would happen is when we come swing down here, if we steer the craft right, we can actually bleed the speed off by doing an aerobraking maneuver and then exit the atmosphere when we've bled enough speed off to get this all the way down to pretty much the top of the atmosphere. Now we could do that, but that's a little bit more advanced a topic that I don't want to do for this scenario. And to be honest, this stock Delta glider is not a really good example of an aerobreaker because we can't adjust the center of gravity. I'm really good when it comes to XR aerobrakes. I do them all the time. So, okay. So the next thing that we're going to do is we're going to circularize the burn to kill off all the velocity that we just created at the lowest point of the orbit here. And it's going to be high. It's going to be something like... hold up a second. I'll tell you exactly what it's going to be. Okay, so we're going to be going about 9610 meters per second, and we'll need to slow down to about 7800. So we have quite a bit that we need to kill off, so we're not going to perform the burn exactly at the perigee. What we're going to have to do is we're going to have to stop a few minutes beforehand and recalculate exactly how long it's going to take to burn the engines. Holy cow, look at how bright Venus is. Directly underneath the Earth towards the bottom of the screen. Wow, I can actually see its phase. It's got to be closer to the Earth than it usually is. Holy cow, that's bright. It's so bright it actually looks like it's a distant moon of the Earth. I mean, when you're orbiting the outer planets, that's kind of what it's like. When you see a moon, it's usually a dot in the sky. It's not like what most people do in art stuff and make it so that you can see the moon at the most convenient viewing angle and viewing altitude and all that. I've stopped a little bit beforehand, just about 8 minutes out. So what I'm going to do is I'm going to display the orbital hack equation. This equation will basically reveal almost everything when it comes to delta V's. Now, that's not true because it won't do plane chains. But it does almost everything. So using the Vis-Viva equation that's on the screen, what we need to do is we need to plug our semi-major axis in for A. And you need to make sure that you're using radials, not altitudes. So you see it's way off if you do altitude. So the semi-major axis is going to be 18.96 e to the 6. And the R is going to be our current radius, which is 7.03 e to the 6. And the mass of the Earth, which is going to be substituted in for M, is 5.97 times 10 to the 24th kilograms. And the value of G is 6.67 times 10 to the minus 11 kilograms cubed per second squared or something like that. And so what we find is the velocity is, or the V is 9610. What is that number? That number is your actual speed when you reach perigee. This is important because that's the point of the orbit that you actually want to manipulate. So if it's 9610 meters per second, how do you find, if you want to circularize, what your orbit's going to be? Very simple. Just drop A to the A you want. If you have a circular orbit, your A is exactly the same as your apogee and your perigee. So take the value of R that you used in the first equation and also use it as the value for A in the second equation. And so now what we find is the velocity that we want is 7530 meters per second. Okay? And now you subtract them. We're going to get just about 2 kilometers per second that we need to kill off. Again, open up your info. Find what your current mass is, 15,940, and your thruster rating is 320 kilonewtons. So A equals F over M. So that's going to be equal to 320,000 divided by 15,940, which is our current mass. And now what I find is we can do 20 meters per second. So we need to kill off just about 2,000 kilometers per second at 20 meters per second, means approximately 104 second burn. So if you want to add in a little bit of leeway because we're going to get lighter, we can round down to 100. Now, if you use calculus, which I'm going to explain in the later episodes, because there's no way you can reach the outer planets without doing calculus. Unless you have fuel disabled, because you really have to get it right. So divide by 2 because we're accelerating. So what we're going to find is we need to start the burn 50 seconds before we hit periapsis. So that's going to be about 250 seconds from now. So basically at this time you can turn retrograde, and once we swing down to periapsis, we're going to do a long retrograde burn, because retrograde will slow you down, which gets you down, which eventually speeds you up. Well, no, we've already done the speeding up. Well, actually, we never did do the slowdown portion. So if we had circularized when we were really high up, that would have slowed us down. And then if we had gone into the orbit we are now, that would have sped us up. So we've actually done all the speeding up that we need to do. Okay, so we'll just sit here until about 50 seconds out from the node. Okay, you know what? I changed my mind. Here's what you should do. If you're in this situation where your orbit's really high up, what you should do is you should sync orbit, choose Mir, and do ship periapsis. And what that's going to do is that's going to give you a DT min value. So what you're going to do is while you're decelerating, you're going to get some good DT min values. And you don't have to kill off all your speed, because what we're trying to do here is sync up with Mir. So this might be better done calculating, but again, I want these tutorials to not be math heavy in the beginning. Once you know what you can do with your intuition, then we can focus on what you can do with math. So again, activating the retrograde autopilot. We're just about 16 seconds out from the burn. 10 seconds. 5, 4, 3, 2, 1, 0, -1, -2. Okay, so watch that DT min value. And we'll see if we can get anything that is really nice. Hopefully we do. Okay, so it's coming down again. 900, 600, 300. Do I want to stop? Boy, that's close. You know what? We're not going to stop here. We could have stopped, but I really don't want to, because it's going to require that we kill off. Yeah. It's just going to require too much math. I don't want this to be math heavy. Okay, let's see. We're about 1 kilometer per second. I think we can get away with that. Let's fix this. So we're going to get that down to 0. And we can also use this extra height as an opportunity to synchronize our get rid of the what little plane changing we need to do. So we can ignore that for the time being. What we're going to do is we're going to come up to the node here, and we're going to fix our relative inclination so that it's 0. Actually, you know what? Let's see. Our node is actually in a different location than our equatorial node. So I think if I do projection target, it'll actually show... No, it won't. Interesting. Okay. Let's get rid of that, because that's kind of distracting me now. It's not important right now. So it's going to be way more fuel efficient if we do the ascending node, but, I mean, you're talking about a 4.5 second burn, so it doesn't matter. I'm going to fix it the descending node. Then we're going to swing around to apogee and keep that orbit sync. So disable the autopilot, and we're going to swing around to the descending node. Okay. So again, concept check. We're at the descending node. We want to lower our relative inclination, which means we need to go up to prevent us from going down, which means orbit normal plus. And it looks like for once, we're actually going to face the orientation that we want to face. So in space, with a real space shuttle, well, not true. You would actually want to expose the hull to the sun and expose your radiator to night. Let's see how much time. We got 20 seconds. Okay, it's going to be a little burn. That's it. We are done. So disable. We should be done aligning the planes now. When we go back to sync orbit, we're going to wait until we get up here at apoapsis. And then we're going to synchronize. Now, we are using ship periapsis, so what's actually going to happen here is we're actually not going to be meeting Mir directly on. So we might be able to try getting away with going to target intersection 1 or intersection 2, and then lower the orbit to the point where it does intersect. That might work. Okay, so we're going to the ascending, not the ascending, we're going to apoapsis. So I intend on burning retrograde, but if it doesn't work, we're going to have to go prograde. So what I'm doing is I'm actually going to use the retro engines because we're very high. It's not going to take much retro to lower our orbit. You notice the orbital speed is 4.6 meters per second, so all all changes to that orbit vector, because that's what it is. It's a velocity vector. You're changing a velocity vector. When the magnitude of the velocity vector is much lower, then a much lower magnitude is required to induce it. So if you want to make your velocity turn right, it's very easy, and it's exactly the same as a car going down the highway. When you're racing a car down the highway, you can't just turn left. You'd go spinning, or you'd go up against the side of the car. You have to slow down, and then it makes it very easy. It makes it very easy to be able to turn, and that's because your magnitude's small. Okay, so what we're going to do is we're going to change mod to we're going to do intersection 1, and let's see if this works. Okay, for this I actually do want to see Mir. Our retros are not very powerful, mind you. Okay, we're at 450. Let's see what intersection 2 looks like. Not much better. And that's getting worse. That's getting worse too. Shoot. Okay, so what we're going to do is we're going to go to this point, and then we're going to burn until intersection matches. So we're going to go down to the periapsis. Here's a beautiful shot of the Atlantic Ocean. Okay, so now this sort of don't know what's going on stuff doesn't happen in real life in space. What you do is you calculate. In fact, I have calculators that can do this for me. Now, with this kind of visualization tool, you're kind of making it so that you don't have to do math. Most things in space, most maneuvers can be solved graphically, so you don't need to use math for most things. But that is not necessarily the case all the time. And it would be nice if this thing had a hypothetical transfer, so that you could see how it induces your orbit. Let's see, 418, and this one is 479. So notice the target. It's going to take longer for Mir to get there than us, so we need to give Mir more time. So this is going to be a pro-grade burn. What we're doing is we're raising our orbit, which is going to extend our period so much so that by the time we come back, we'll have delayed and allowed Mir to catch up again. And now that we have an intersection and our relative inclination is somewhat low, we will actually be able to meet. And we're actually on 0 orbit, so if you can believe that, we're actually coming around for the meet next orbit, even though we're so far apart right now. Okay, let's see. 15 seconds out, we can burn now. Whoops, overburn.
Translation.
And that's the thing too, is you know, if you're math heavy, these things can be very, very accurately planned. But I know most people are kind of, you know, they don't like math, and you know, I can understand that because it makes you think. So I'm trying to avoid the use of math for as long as we can, and then hopefully teach a little bit. You know, you don't really have to understand it if you can just plug the. If you know how to do algebra, you can just plug the formulas in. The sole exception being calculus, and most of the calculus isn't very hard. Okay, that's it. We're going to go to the apoapsis, or relatively close. It looks like our relative inclination has creeped up again due to the fact that we're at a much higher altitude. The other gravity sources are tugging on us, and we're being moved out of alignment. So we need to align our planes again. And let's see, 2-second burn, we're going to do it at descending. Well, actually, no, let's do it at ascending because it gives it less time to mess it up. So we're going to the ascending node now. Okay, we're at the ascending node. We're trying to lower our relative inclination. So to stop us from going up, we need to go down. Orbit normal minus. And there's a beautiful shot of North America. Although I don't think that storm would be over central Canada. That's pretty rare. So 0.5 degrees, that is high. If we didn't fix this, we probably wouldn't be meeting, at least on the same where we want to meet. We'll be chasing Mir around. And so if you burn with your engines half, you will actually be receiving or you would be starting your engine at exactly when this says time to thrust. Because when you're accelerating, the time-velocity relationship is over 2. Okay, so there's nothing we can do there. Let's go to sync orbit. We're going to be about 6 seconds off. So let's go ahead and fix that right now before it becomes unrecoverable. We're going to turn prograde now. And it looks like... yeah, see, this is that weird situation where you're between apogee and perigee. So if you don't use differential equations, it's really hard to know precisely which way you're going to go. So let's try and see what happens. Okay, that's the wrong way.
Rotation. Translation.
Done.
Rotation.
Okay, so disabling the autopilot, we're going to save, and now we're going to do one more calculation. So go back to your vis-viva equation that you were so kind to write down. And we look at our new semi-major axis. We didn't kill off all the speed before, but we're going to have to now. So our semi-major axis right now is 10.08 times 10 to the 6. And Mir... our point of intersection is going to be roughly 300 kilometers. So that's gonna, let's change this back here. It's gonna be about, let's see, between 6686 and 6653. So 6.676 e to the 6. That's a lot of 6s. Okay. And we're going to have a velocity of 8939. Now use that value of r in A, because that's what happens when we circularize. 6.68 e to the 6. Okay. And we get 7731. So we got 8939 and 7731. Again, do the exact same thing. Whoops. Open up your info. Now we're 15,411 kilograms. And now we get a Acceleration of about 20.76. But for calculus sake, we're going to round up to 21. Be careful when you round like that. We have a velocity of 1208 meters per second. To divide by that time, we're going to be about 57. It's going to take 57 seconds to kill. That's your t squared. So 0.5 times a, which is going to be 21, times t squared. And we're going to have to start the burn 35 kilometers out from Mir. That's when we're going to start the deceleration burn. Long time. So we're going to go until we're just a few minutes out from the meeting point. Okay, we're 5 minutes out from the meet. You know you're bang on when you hit 35 kilometers exactly, let's see, half of that time. So exactly 28 seconds out from the meet. If you're at 35 kilometers, you were bang on. But we do have a little bit of relative inclination difference, so that's going to result in a not exact meet. If you really wanted to, you could figure out what that delta would be, and then you would know precisely, you don't burn at 35, you burn at 38, because by the time you finish your burn, you're still going to be 3 kilometers out until you do a nearby one. But anyway, press F4, go to Info. Under Object, you want to click the drop down, go to Vessel, drop down to Mir. Okay, and Mir has a transponder of its own. It is 132.10. And we've got Mir on the radio. And on nav 2, let's see if there's any docking ports. All 3 ports are free. 135.0 is docking port 1. Again, the docking is a closer in one, and we're on nav 1. Perfect. It's time to go to the dock. And we still have our nose cone open. So we're about 265 kilometers out now. And pretty much now it's going to be a good idea to turn retrograde. But before we do that, let's see if we can adjust this a little bit. Keep us on track here to meet precisely. There we go.
Rotation.
You can never sync orbit too many times. Again, you can't use the retrograde autopilot to do this. So in just about 100 seconds from now, we'll be stopped at Mir, and we're currently 90 miles away from it. Pretty incredible. And it should be coming into view any second now. Can't see it just yet. Let's see how close those... Yeah, the velocity vector is pretty darn close. So if you want to get more accurate You could induce the velocity vector by burning retrograde and downwards. That will cause the velocity vector to migrate down here, and you'll meet it directly. Okay, I can see Mir. Okay, time to watch the clock. 45 seconds. 40 seconds. 37, 36, 35. Okay, time to hit the engines. So we're not going to stop actually directly at Mir, but we're going to come pretty close. Doing pretty well. Let's see how we are. Yep, that's right about where we want to stop. Okay, so you'll notice we're still about 6.5 kilometers away, and we're not actually going to go to Mir the way it is now, and that's because of the residual relative inclination of 0.07 degrees. But that's okay. We're close enough now that we can actually do Mir direct. So I'm going to be aggressive with this and burn my engines again to get closer to Mir. So go to info, and we want to look at the retrograde. We have 68 kilonewtons, so 68,000 divided by our current mass, 14,851. Whoops, that is not a division. Okay, so we can only induce 4.5 meters per second. So actually, we're getting too close. We're just actually going to have to kill the speed with our engines, like now. Alright. Okay, that was cutting it too close. If I didn't do something right there, we probably would have contacted. Oh geez, we're that close. Oh yeah, 800 meters, that's still close enough. So just keep on your retro velocity vector, and when you get close enough, you can just keep killing. 20, 310, 300, 290, 280, 270, 260. Alright, right there. Alright, when you see that starting to turn around, then you know you're done. Alright, nav 2. HUD, and now we should have a docking port. Check the nose cone is out, and we still have our docking lights turned on. So let's repeat the exact same procedure with Mir. Pick a box and go for it.
Translation. Rotation.
So center yourself within the box, and then once you've killed off most of your speed, then you can turn to face the docking adapter.
Translation.
Next thing you want to do is actually center yourself within the box.
Rotation.
It's a good idea to start further out from the craft, but when you get better, it's just not necessary. Alright, so at this point what I'm doing is I'm centering that red X on the crosshairs, and I'm centering that white triangle on the top. That means we're lined up.
Translation.
So now we're coming down to the docking adapters, so you see the gold cross. I'm lining up my velocity vector with that gold cross. And the velocity vector is the gold arrow. And we're just about there.
Rotation.
Whoops.
Translation.
Don't mix up your translation into rotations. We're actually at a pretty healthy advancing speed right now. So we're just about 120 meters out from the docking adapter. So in the interest of time, I'm going to stop the video from now and come back when we're closer. But it's basically this, right? You're keeping your X aligned, keeping the cross aligned, and keeping that triangle where it's supposed to be, and you'll dock. Okay, we're much closer now. We're within the final box. And our light should begin to illuminate
Rotation.
Mir.
Translation.
I wonder what this strange orange thing is. I know it's not. It's definitely not docked to the docking port because all three docking ports show that they were available.
Rotation. Translation.
To some degree, you can actually do a visual approach if you want to.
Rotation.
But it's a good idea to do the instrument. Okay, we're getting too close now.
Translation.
So let's go ahead and slow that down.
Translation. Rotation. Translation.
Okay, we need to stop.
Rotation. Translation. Rotation. Translation.
Alright, we're 4 meters, so I'm slowing to contact
Rotation.
velocity. And we should be able to just roll straight forward now. Three, 2, 1.
We show capture and hard dock. Congratulations.
They should change that so that you get like a Russian message, because we've just docked with a Russian space station. Okay, so that's pretty much it. We could repeat the same procedure as before with, you know, equalizing and everything, but I don't really see a point in doing that. That's not really needed. So that's pretty much it. So in the interest of keeping this episode, you know, to a reasonable time, we'll go ahead and end here. But This is us docked with the Mir space station. And I think for the next episode we're gonna leave it here and start fresh from the ground again. No need to show re-entry because the procedure is exactly the same. As soon as you depart from the internet or from Mir and move away from it, re-entry, descent, and landing is exactly the same thing as it was before, just with a different set of orbital parameters. Other than that, besides the undocking, it's seamless. So thank you guys for joining me, and I will see you guys next time for my next tutorial, which hopefully is really exciting. Bye-bye.